Traveling in time appeared in many sci-fi movies, but every law of physics claims that the only way we can move through time is forward. Well, thanks to some very exciting properties of space and time in Einstein's general relativity, going back in time seems to be possible after all. According to Einstein, space and time are not separate entities. They're woven together in the fabric of space-time. There's also a quantity that generalizes the concept of distance into 4 dimensions, the space-time interval. It takes into account distance in time. In other words, if you're resting, your spatial position doesn't change and you're moving through time forward at 1 second per second. But if you're moving and your spatial position changes, you travel through time more slowly. All because objects in relative motion experience something known as time dilation. Roughly speaking, the faster you travel through space, the more slowly you move through time. More precisely, time dilation is the difference in elapsed time as measured by 2 clocks because of a relative velocity between them. The faster the relative velocity, the greater the time dilation between them, with time slowing to a stop as 1 clock approaches the speed of light. However, keep in mind that we only know about massless objects, such as photons, that travel at the speed of light. Theoretically, if you could move faster than the speed of light, you'd become a tachyon, a hypothetical particle that always travels faster than light. Also, there is the energy-momentum relation that connects energy, momentum, and mass. One can see from that relation that if a particle moves faster than speed of light, then its mass is imaginary. So, this possibility is an unphysical situation, since tachyons don't correspond to anything that exists in our physical reality. However, Einstein thought that going faster than the speed of light wasn't the only way to travel backward in time. Space-time might not be flat and unchanging. It can be curved, can contract and expand, and can even create and maintain a connection between 2 different points within it. This possibility is known as an Einstein-Rosen bridge. If you jumped into one point and your friend jumped into the other, you could meet somewhere in the middle. At the same time, this tunnel wouldn't be passed through, and you wouldn't be able to get out on the other side. Now, try to imagine space-time as a 2-dimensional sheet of paper. If you fold it, 2 points that were previously separated will become connected in this new 2-dimensional world. This property of space-time might be the most important concept of time travel. You probably know this concept under the name of a wormhole. And it's tightly linked to black holes, regions of space containing so much matter and energy that any light emitted from that region, as well as any matter and radiation that falls there, will never escape. And it doesn't matter how much energy it has or how fast it's moving, even if it's the speed of light. Usually, it's assumed that black holes only lead to a central singularity, and if you fall behind the event horizon, also known as the point of no return, there is nothing but destruction awaiting you. But how about another possibility? What if black holes could actually transport you to another universe? Then, you would be expelled on the other side through something called a white hole, a time-reversed solution of a black hole. But so far, all this sci-fi theory is just a hypothesis. What we do know is that minuscule quantum fluctuations exist in our known universe. They occur throughout the fabric of space-time, most prominently on the tiniest of scales. Such energy fluctuations can occur very close to one another. They are most likely random and often include disconnections and reconnections from the original positive and negative states that initially occur together. If you somehow connected such positive and negative curvature regions together, you could get close to the notion of a quantum wormhole. And if such a wormhole remained intact for a long enough period of time, you could transport a particle through it. In other words, it'd instantly disappear from one location in space-time and reappear in another. But why is a wormhole so crucial when we talk about time travel? Because once you create 2 ends of a wormhole and maintain the connection between them with sufficient mass and energy, this connection will remain eternally. And since this is great for instantaneous travel through space, probably we could extend it to traveling through time too. Sadly, at the moment, it's just wishful thinking.
Okay, so you've seen the movies and read the books on time travel. Most of them tell stories about entering some futuristic boxes, and in the blink of an eye, you're in some different epoch. For now, this is just sci-fi. But there are ways to make time travel possible, at least theoretically. We just don't have the technology figured out yet. For starters, time travel to the future could be achieved by traveling at high speeds, but not just getting a ticket on the superhighway kind of speed. This is based on Einstein's theory of special relativity. It explains that time slows down for objects that move at really high speeds. And the good news is scientists have already tested this theory, and it looks promising. They did it with the help of two identical clocks. One was placed on a jet, and one stayed on the ground. They found that the clock on the jet ticked slower than the one on the ground because of how fast the jet was moving. The faster an object is moving, the more time will slow down for it. Currently, the fastest speeds achieved by human technology are seen in a special type of particles called neutrinos. Some of these can move at almost the speed of light. At these speeds, 1 second for the protons is equal to 11 months for us. Now, we might be able to time travel to the future with the use of gravity, too. This idea is based on Einstein's findings, namely his theory of general relativity. Now, this theory explains that the stronger gravity is, the more slowly time moves. This means that as you get closer to the center of the Earth, the strength of gravity increases. And if you think about it like that, time actually passes more slowly for your feet than for your head. Now, is that why I'm always late for stuff? Good excuse. This effect has been measured too, with the help of the same strategy with two identical clocks. Scientists placed them on shelves at different heights and measured the rate of ticking. The clock on the lower shelf ticked more slowly because it experienced a slightly stronger gravity. But this option comes with a catch. To be able to travel to the far future, you'll need to find a place with extremely strong gravity, like a black hole. That's a point in space where the gravity has so much force that even light cannot escape it. There, gravity becomes so intense that matter gets squeezed into a tiny space. The closer you get to the black hole, the more slowly time moves. However, traveling via a black hole is very dangerous, mostly because it's a one-way ticket. Once you cross its edges, there's no coming back. Now, here's a fun fact. The GPS systems we use on our phones and in our cars already have to account for time dilation effects in order to work properly. That's because of the speed of the satellites they use and the gravity they feel here on Earth. Without these corrections, your phone's GPS wouldn't be able to pinpoint your location on Earth very precisely. Meanwhile, the third option has less to do with the universe's unknown forces and more to do with our own bodies. Scientists are trying to find ways to time travel to the future by slowing down the body's own processes. It's not time travel per se. You wouldn't technically be going anywhere. But if your body stays put for a long period of time, you could eventually wake up in the future. Some animals, like bears and squirrels, can slow down their metabolism during hibernation, which means they don't need as much food and oxygen to survive. Specialists are trying to figure out if humans can do the same thing. They're working on ways to make people go into a short-term hibernation for a few hours to begin with. This could be helpful for medical emergencies too, in order to help a person before they can safely get to the hospital. In 2005, scientists were able to slow down the metabolism of mice by exposing them to a small amount of special gas. However, when they tried to do the same thing with larger animals, it did not work as effectively. Our fourth option of traveling through time is really unique. It involves a special type of shortcuts that may exist in our universe called wormholes. Now, before we move on, let's try to understand what they are. You'll need to picture two balls and a trampoline. If there's no pressure applied on the trampoline, it stays flat. Now imagine the two balls placed on the trampoline symmetrically. If you look at them from this perspective, there's no possibility of them ever touching. But if you put enough pressure on the trampoline between the two balls, this flexible fabric can stretch so much that the two objects might potentially touch each other. The same thing happens with stars in different star systems. They're big enough to curve space around them. That's why most planets tend to orbit around a star. The tunnel between those 2 points would be a wormhole. These wormholes could be used to travel long distances, like 1 billion light years, or even visit different times. Now, many scientists, like Stephen Hawking, think that wormholes might appear and disappear, but be very small, smaller than atoms. The problem is that we don't know how to catch one and make it bigger so that people can use it. This would take a lot of energy, and we don't know if it's even possible. Some astronomers say that even if we could find a wormhole and enter it, it would rapidly collapse on itself. Even the tiniest bit of extra mass, like that of our bodies for example, can result in the wormhole slamming shut, like a rubber band that's been stretched too much. Now, the fifth solution for time traveling was proposed by an American physicist named Ron Mallett. It involves one resource that we know for sure is abundant in the universe – light. The scientist proposed a theory about time travel that would use a rotating cylinder of light. He believes that if something was dropped inside this swirling cylinder, it could be moved in both space and time, similar to how a bubble moves when you swirl it with a spoon in your coffee. According to Mallett, the right shape of the cylinder could allow for traveling to both the past and the future. The physicist has been trying to raise money for an experiment to test his theory. This experiment involves dropping tiny particles, called neutrons, through a circular arrangement of spinning lasers. However, other scientists say Mallett's theory is impossible and there's no need to test it further. Well, even if we eventually figured out a way to travel back in the past or to the future, would it be safe? Scientists have been talking about a problem called the paradox of time travel for a long time. The main question is what would happen if you went back in time and did something that changed the future. However, a new study from researchers from the University of Queensland says that this problem might not be real after all. The scientists have done some calculations and found out that even if you had changed something in the past, the timeline would still end up the same way. Another variation of this problem is called the grandfather paradox. Imagine going back in time and preventing your own grandfather from having offspring. Come to think of it, it automatically means you shouldn't exist in the first place. If your grandparents didn't have your parents, how can you exist at all? Well, these days scientists are certain that even if you did experience something like that, you'd still exist in the present. That's because the timeline that already exists has a way of adjusting itself, regardless of where people are in time and what they do. Or somehow get 1.21 gigawatts in a DeLorean and make like Marty McFly. You of course know that the Earth is bathed in sunlight every day. Every day we flicker different light sources on and off, mechanically, without even thinking about it. But imagine that one day you casually flicker the lights off, fall asleep, and wake up in a completely different era. Let's see how it happened and what it has to do with light. Quantum physics is quite crazy. Classical physics is like a movie projected from start to finish, while the quantum world is like having an ability to take the remote control and manipulate scenes you're watching. Fascinating and mysterious. Let's say you have a regular light switch that can be either on or off. That's like a regular bit in computers, which can be in one of two states, 0 or 1. But in quantum computers, there's a special kind of switch, a switch called a qubit. Unlike the regular bits, a qubit can exist in multiple states at the same time. It can be both 0, 1, and all things in between, like having lights on and off simultaneously. Yeah, our universe has some weird rules. This mysterious property, called superposition, allowed us to do something incredible recently, to reverse time back. At least in a tiny experiment with quantum computers. It's the autumn of 2022. Two groups of scientists, one from Oxford and the other from Vienna, decided to conduct a weird experiment. They played around with a quantum computer to create a program that reverses time. They took a tiny electron and tried to make it go backward for a time for just a fraction of a second. It would be like breaking a billiard ball triangle, where the balls go from order to chaos and then magically reverse. But don't get too excited about time travel yet. Unfortunately, we're not sure if it's possible to recreate it in real life. The scientists cracked some numbers and found out that if we observe 10 billion localized electrons every second for the entire age of the universe, we'd only see something like this happen once. and it would only take the electron back a tiny fraction of a second. So they didn't invent a time machine. They just managed to create this simulation in quantum computers. There's another catch too. The larger the simulation, the more complex and less accurate it becomes. In our experiment, we only used 1 qubit and we managed to reverse time. In a 2-qubit setup, scientists could reverse time only in 85% of cases. And in a 3-qubit setup, it dropped to 50% with more errors. If we keep adding more qubits, we won't be able to pull this off at all. Plus, the success depends on the amount of information the system can store. For example, teleporting a person would be almost impossible because humans have so much information inside them. So, unfortunately, no time machine so far. But there are some possible uses of this discovery. Reversing qubit states in a quantum computer can help correct errors during development, sort of like a little Control-Z in real life. So, it was a tiny step to more exciting discoveries in the future. For example, recently they demonstrated another crazy little thing: send light itself back in time. Now, light isn't mere luminary. It has superpowers that we can't even imagine. The ancient Greeks believed that our eyes emitted visionary beams. Sir Isaac Newton proved them wrong hundreds of years later when he conducted his experiments with prisms. The prism broke the pure white light into a beautiful palette, and that's how we found out that light actually consists of tons of different colors. Many years later, scientists learned even more, that light is a wave. And even later, in the 20th century, we discovered the final paradox, that it's both a wave and a particle, a dual existence in one photon. And the more we learn about light, the more crazy things we find. In 2016, scientists managed to freeze the light in time. They put photons, the tiniest light particles, in ultra-cold atomic clouds. Then they managed to stop it, again, for just a moment. But the fact that it's even possible is already incredible. Then scientists got even bolder. They decided to try not only to freeze the light, but to move its direction in time. They took a special crystal and passed a photon through it, thus initiating the so-called quantum time reversal. As a result, the photon started moving into both the future and past at the same time. The science magic behind this involves 2 quantum principles: superposition and quantum symmetry. We already mentioned the first one. It allows tiny particles to exist in multiple states at once. Now, the second principle says that even if you flip particles around like a mirror, they'll still follow the same laws. Combining this, scientists crafted a photon that defied the usual forward march of time. But again, it's nothing super fancy yet. This time flip only works for specific particles, not entire humans. And even if it did work for us, rewinding a person even for a second would take a super long time and a lot of energy. But the fact that we can change the light's speed and make it change directions is already amazing. And scientists already see some possible applications to this. For example, Harvard researchers suggest a cool way for spacecraft to zip through space at the speed of light, by hitching a ride on supernovas. Usually, traveling to other stars takes an insane amount of energy, but these scientists have a wild idea. They think that spaceships could use natural events like hypervelocity stars and meteors zooming from supernovas to reach super-fast speeds. It's kind of similar to how sailing ships catch the wind. Advanced civilizations could use these energy bursts to speed up their spacecraft. Imagine a cool spacecraft with solar or magnetic sails harnessing the power of a supernova boom. These sails could use the pressure of the sun's radiation to work, so that we wouldn't need any traditional engines or fuel. Plus, these sails concepts are much lighter and cheaper to launch into space compared to regular spacecraft. The team is already working on a light sail accelerated by lasers to reach 20% of the speed of light. It might not sound like a lot, but it's actually an insane speed. Their dream is to help humanity make a swift journey to Alpha Centauri in just 2 decades. Isn't it amazing how many things we can do with light, and not just in our imagination? Let's go to more practical achievements. Recently, a Canadian camouflage company called Hyperstealth Biotechnology Corporation has crafted an actual invisibility cloak. The wizardly cloak doesn't need any power source, is as thin as paper, and won't break the bank. Hyperstealth envisions a world where this material can cloak people, vehicles, ships, spacecraft, and even entire buildings. It's still in a prototype phase, but it already works pretty well. They name this incredible technology quantum stealth. It bends light in a way that can make objects disappear from sight. It can render objects nearly invisible, not only in the visible spectrum, but also in ultraviolet, infrared, shortwave infrared, and it even throws in thermal spectrum blocking for good measure. The technology works thanks to the lenticular lens, a corrugated sheet with outward curving lenses. When stacked in a specific way, these lenses refract light at various angles, creating spots that block light and conceal the object behind the material. Unfortunately, it doesn't give you a full invisibility effect, but maybe someday we'll achieve it, if we keep working on it. If you hide behind it, it will look like a little dirty or blurred glass, but you won't be visible. If you put this veil in front of your body, you'll look like a floating head. Scientific progress is in full swing. Maybe one day we'll be able to reverse time not only for little light particles, but for entire humans. Until then, let's enjoy our invisibility cloaks and stay curious.
Time runs like a river. It has direction, always advancing. It has a certain duration, periods between events you can measure. Time feels real, always there, unstoppable, moving forward. But what if I told you that time might not exist? Some physicists and philosophers claim that there might be no such concept as time, and we should take this possibility of the non-existence of time seriously. You see, recently physics has been in crisis. For the past century or so, two extremely successful physical theories have been used to explain the universe. Those are the theory of general relativity and quantum mechanics. Quantum mechanics describes how things work in the super tiny world of particles and their interactions. As for general relativity, it provides an outlook on the bigger picture, for example, gravity or how objects move in space. And even though both of these theories seem to be working really well, they are believed to conflict with one another. That's why some scientists think that they need to be replaced with a new, more general theory, like quantum gravity. This idea might be able to explain how gravity works at the miniature scale of particles. Apparently, it's incredibly difficult to produce the theory of quantum gravity, but it might be possible to do it with the help of string theory. It replaces particles with strings, vibrating in 11 dimensions. But there's one problem. Even though string theories do provide several models describing the universe, they don't make any clear predictions that can be tested by experiments to understand which model is the correct one. There's one more idea known as loop quantum gravity. According to it, the fabric of space and time is made of super tiny chunks, loops. But the most remarkable aspect of this theory is that it completely eliminates the concept of time. Now suppose this idea turns out to be correct. Will it mean that time doesn't exist? Well, the answer is kinda complicated. Everything depends on what the word exist means. A philosophy professor from Cambridge University claims that the three basic properties of time, a present moment that is special, the flow of time, and its direction, come from our mental states and not from the physical world. So we sense this arrow of time because our minds add a certain subjective ingredient to reality. At the same time, Einstein's theory of relativity supports the idea of the block universe, a four-dimensional space-time structure where time is like space. It has its own coordinates in space-time. Time is tenseless there. Thus, the future and past are as real as the present. Does it mean we're being fooled by our human perspectives? Is the feeling that time passes and has a certain direction false? Well, we can imagine our world as a three-dimensional place where stuff happens gradually over time. Or it might be a four-dimensional space where nothing actually happens because nothing changes. It's all here at the same time, past, present, and future. The main idea of relativity is that there's no absolute space and no absolute time. Everything is relative. Trying to think about time in the context of the universe, you realize that you need to isolate part of it and call it, let's say, your watch. And time is basically the relationship between some parts of the universe and that thing you called your watch. Another scientist says that time is just a collection of snapshots describing our reality while continuously changing one into another. Here, you hit play. Here, you're blinking while watching this video. And here, you're taking a sip of your coffee. Without these changes, there wouldn't be any notion of time. The changes are real, but time is not. Our brain sees these changes and constructs a sense of time, believing that it's flowing. What do you think? Is time just a social construct, or does it really exist?
Even though it may seem that science has reached the level where there are no more mysteries left, it's not exactly true. And no modern physicist would dare to assume that our knowledge of the universe is near completion. What are scientists still wondering about? Let's figure it out. For one thing, dark energy keeps puzzling researchers even today, because the universe doesn't seem to add up. Even though gravity is pulling space-time, the very fabric of the cosmos, inward, the universe keeps expanding outward, and this process is speeding up. That's how the concept of dark matter was born. It's believed to be some invisible agent that counteracts gravity by pushing space-time apart. It goes like this. The universe expands, and more space appears out there, and with it, more dark energy. According to astronomers, this invisible energy must make up more than 70% of the universe. But no one knows how or where to look for it. Then there's dark matter. You see, around 84% of matter in the universe doesn't emit or absorb light. Scientists call this stuff, which can neither be seen directly nor detected by indirect means, dark matter. Its existence is inferred from the effects it has on visible matter, radiation, and the very structure of the universe. There are a few special detectors on the lookout for weakly interacting massive particles, of which dark matter might be composed. But so far, nothing has been found. One of the most recent studies claims that dark matter might produce long, fine-grained streams radiating out from Earth like hairs and streaming throughout the universe. But it hasn't been proven yet. Then, there's the question of antimatter. It's the oppositely charged and oppositely spinning twin of good old matter. The intrigue here is why there is more matter than antimatter in our universe. It would be logical to assume that the universe would want to treat matter and antimatter equally. Thus, at the moment of the Big Bang, equal amounts of matter and antimatter should have been produced, right? Not really. If it had happened, there would have been a moment of total annihilation. Protons would have canceled antiprotons, electrons, anti-electrons, and so on. It would leave behind a lifeless, matterless expanse of space. Luckily, for some mysterious reason, when the universe was created, there was some excess matter. It didn't get annihilated, and that's how everything started. But there's still no accepted explanation for this. Then, we've got particle physics questions. They account for many unsolved problems. Sonoluminescence is one of them. Let me explain. Let's say you take some water and hit it with sound waves. It forms bubbles, low-pressure regions surrounded by high pressure. Once the outer pressure pushes on the lower pressure air, the bubbles collapse. But while collapsing, they emit light, even though the flashes don't last for more than a trillionth of a second. What bothers scientists is that it's unclear what the source of this light is. There are a few theories, of course. Some experts think tiny nuclear fusion reactions might be involved in the process. Others believe some kind of electrical discharge comes into play here. There's also the idea of compression heating of the gases inside the bubbles. None of these theories have been accepted yet. This might sound surprising, but we haven't figured out what exactly gravity is either. Other forces are mediated by particles, but not gravity. Some physical theories claim that it might be carried by a hypothetical massless particle called a graviton. But no one has seen these gravitons yet. We don't even know what kind of detector can be built to spot them. Even if gravitons come into contact with matter, and we aren't sure about it, they do it extremely rarely. There's also a theory that gravitons are closed loops of energy, but again, it's just a theory so far. There are tons of other unanswered questions bothering our minds. What happens inside a black hole? Is string theory correct? What is the fate of our universe? Do we live in a false vacuum? Hopefully one day we'll find the answers to all these mysteries.
Hey, ever wondered what's bigger than infinity? Infinity plus one? Nope. It's not even infinity times infinity. But indeed, there are situations in which one infinity can be bigger than another infinity. I hope I haven't confused you yet. First of all, we've got set theory. That's when you take a group of something and put it into a defined set. For example, 5 pencils. But it can actually be anything. It doesn't matter. What matters is there is stuff in the set. Okay, you might be wondering, how can it help me understand infinity? Let's try to somehow define the size of the set. Well, it's easy to understand that the size of a set of finite elements is simply the number of these elements. But how should we think about the size of infinite sets? Oh, let me introduce correspondence to you. This is a concept in set theory that functions by relating one individual object in one set to another individual object in another set. These individual objects can be some items or just numbers. The main thing is that each item in one set can be compared to an item in another set. For example, 2 pencils to 2, 4 pencils to 4, and so on. We cannot compare the sizes of infinite sets, but we can define correspondence between elements. And if 2 given sets have a one-to-one correspondence between their elements, then these 2 sets have the same cardinality. Roughly speaking, the word cardinality means numbers of elements. If the cardinality of some infinite set is equal to the cardinality of the natural numbers 1, 2, 3, 4, 5, 6, we call the power of this set Aleph 0. Let's stop here for a moment and do some math. Do you still remember our main question? Right. How can one type of infinity be smaller than another? But what if we use 2 different sets of counting numbers, which are also called natural, and imagine that both these sets extend forever? Set A, 0, 1, 2, 3, 4, 5. Set B, 1, 2, 3, 4, 5, 6. As you see, set B starts one number higher than set A. But we have one-to-one correspondence between sets. It means that they represent equal types of infinities. In other words, each number in set A corresponds to another number in set B that is one value higher 0, 1, 1, 2, 2, 3, etc. Now this is the smallest type of infinity, the very Aleph null. Okay, another question remains. Why isn't infinity? Let it be Aleph null plus 1 bigger than good old Aleph null. Well, here's another example. This person is a cyclist. We take his bike, use it as a +1, and put it in set A. Now, our sets look like this. Set A, bike, 1, 2, 3, 4, 5. Set B, 1, 2, 3, 4, 5, 6. Following the logic, we match the bike to 1, 1 to 3, 3 to 4, and so on. As you see, it's possible to keep this one-to-one correspondence between the sets, and it can go on forever. It means that infinity and infinity plus 1 indeed have the same cardinality. But wait, it gets even weirder. Picture building a set using only natural numbers ending in 0, 10, 20, 30, etc. Then you compare it to the set with all the natural numbers 0, 1, 2, 3, 4, 5, etc. At first glance, it seems that the second set should be 10 times larger than the first one. But as far as the set theory is concerned, these 2 sets are equal. Amazing, isn't it? Then how can any infinity be bigger than another one? To figure it out, we need to enter the world of real numbers, which are any numbers representing a quantity along a continuous line. It can be 59, 4.335,081 pi, any fraction that comes to your mind, and so on. Imagine 2 points on a line. Between these very finite points, there's an uncountable and infinite set of numbers. Long story short, just trust us that mathematicians can prove that it's impossible to create a one-to-one correspondence between natural numbers and every possible real number. Here you go. With the help of sets, we've found an infinity which is bigger than the infinity Aleph null.
Everything around us, as well as all living creatures, consists of atoms. That's what we all learn at school. atoms come in around 100 types, called chemical elements, and are typically arranged into molecules. We take this fact for granted, but let's say, in the 19th century, the existence of atoms was still hotly debated. And even today, there are some details in this picture that are kind of fuzzy. Some puzzles baffling people a century ago remain unsolved. And Higgs particles have everything to do with this mystery. It's a known fact that the mass of an atom comes mostly from its nucleus. The electrons forming a wide cloud around the nucleus actually make up less than 1,000th of an atom's mass. But an atom's size depends mostly on the electron's mass. If you decrease the mass of the electron, the size of the atom will increase, but it will also become more fragile. At the same time, if you decrease the electron's mass by even a bit more than a factor of 1,000 or so, atoms will get so delicate that even the leftover heat from the Big Bang could destroy them. The mass of the electron, as well as its origin, has puzzled physicists since it was first determined. Photons, particles that make up light, have no mass at all, but atomic nuclei are made of quarks that do have mass. And there's also evidence that neutrinos, those elusive particles streaming from the sun, have tiny masses too. But then, why do electrons, quarks, and neutrinos have mass while photons don't? To explain it, researchers needed fresh ideas, and in the early 1960s, a possible solution was found: the Higgs mechanism. Imagine an unknown field of nature that is not zero and is uniform all over the universe. If this Higgs field could be of the right type, its presence would cause all kinds of particles to develop masses. This field is invisible to us. We can't detect it using our senses, and it's impossible to detect it directly with scientific equipment. Then how can we learn anything about it? You see, the Higgs field is like air. When you disturb either of them, they vibrate, producing waves. In the case of air, you can create such waves quite easily. Just shout or clap your hands. Your ear will detect the waves in the form of sound. But in the case of the Higgs field, it's extremely difficult to create the waves and even trickier to observe them. To make them, you need a giant particle accelerator, and we have one. The Large Hadron Collider located at the CERN laboratory outside Geneva, Switzerland. As for detecting them, you need special building-sized scientific instruments. Luckily, those are available too. So how can you do it? Smashing two very energetic protons together can create incredibly quiet Higgs waves. Plus, 1 in every 10 billion collisions can do it. The wave that is created is the quietest possible wave in the Higgs field. It's called a Higgs particle or Higgs boson. Producing a Higgs particle is actually the easiest part of the process. Detecting a Higgs particle is the hard part. While a sound wave always travels freely through the air, a Higgs particle disintegrates into other particles in less time than light needs to travel through an atom. All that the scientific instruments can do is measure the debris from the exploding Higgs particle as precisely as possible. After that, they can try to work backward and determine whether a Higgs particle could have been the source of that debris. But it's not enough to create just one Higgs particle, since its debris isn't distinctive enough. A collision of two protons might create debris similar to what might emerge from a fragmenting Higgs particle. Then, how can we determine that exactly Higgs particles have been formed? The key here is that even though Higgs particles are rare, their debris is relatively regular in appearance. It helps researchers pick out the typical ringing of the Higgs field amid the cacophony created by other similar-looking processes. Carrying this out is an incredibly hard and complex process, but somehow humanity has managed to do it. And even though this discovery doesn't mean the end to the puzzle about the masses of the known particles, it gives us hope that we will eventually solve it.
Imagine simultaneously being born, growing up, and getting old somewhere out there in the universe. Sounds bizarre and unrealistic. And still, according to the block universe model of the world, that's exactly what happens with you, me, and other living beings on our planet. It's as if someone drew pictures about every moment of your life and then just piled them one on top of another, creating a giant block of all things that ever happen at any time and at any place. The future, present, and past exist at the same time and are equally real. The block has 4 dimensions. 3 of them are spatial. Its length, width, and height. there's one more: time. To make it easier, let's picture our world as a cuboid, which is basically a three-dimensional rectangle. Its height and width represent two of the three spatial dimensions of the universe. As for the third spatial dimension, we'll replace it with time. At one end of the cuboid, we'll drop the Big Bang. And at the other, there will be the end of the universe. Let it be a big crunch. Our cuboid is filled with every single event that ever happens. Even this moment, when you're watching this video, exists somewhere in the block. Now, we perceive today as the present, yesterday as the past, and tomorrow as the future. From this perspective, it seems that time passes. But in the block universe, time doesn't flow. There's no specific present moment since the notions of the past and future are relative. You see, we are always located wherever we are, which means that everyone remains in the present. But the block universe theory doesn't deny the notions of earlier than and later than. These relations remain no matter what, and regardless of where anyone is located. For example, Molly the mammoth is located earlier than Marcus the tiger. This relation between Molly and Marcus will remain unchanged regardless of whether you're located later than Marcus or earlier than Molly. This way, in the block universe, now is any time you are located at. Past is any time or events that are earlier than your location, and future is any time or events that are later than your location. It sounds like in the block universe, we could travel in time since it's just another dimension. Well, it could be true, but of course, things just have to be more complicated than that. Traveling in time is way more difficult than traveling in space, but it's not impossible if you travel very, very fast. Traveling at extremely high speeds results in time dilation. We can travel into the future at a reasonable percentage of the speed of light, and to get to the past, we can use wormholes, shortcuts through space-time. But if we can travel in time in the block universe, can we change the past? Not really, because if you do, it'll create a contradiction. Keep in mind that, in this universe, the past is the same as the present or the future. What is past to you is future to someone else. And when traveling to the past, you're going to someone else's future. In the past, you'll act just like you do in the present, but you won't be changing the past. All your actions are already predetermined in the block universe. At the moment of the Big Bang, it's already clear that at one point, you'll travel to the relative past. Just like what you do tomorrow makes tomorrow the way it is and has always been, what you do in the past makes it the way it is and has always been. The events in the block universe do not change. As a time traveler, you don't suddenly appear in the past. It's always been the case that you're located in the past. And nothing a time traveler does can change anything in the block. Instead, whatever you do at any time makes that time the way it is.
If the universe is everything, then there is nothing external for it to expand into. But we know for sure that it does expand. So the question is, what exactly is it expanding into? According to the theory of cosmic inflation, the universe was once filled with large amounts of energy. It was similar to hypothetical dark energy, but much greater in magnitude. It made the universe expand faster and faster. As a result, the universe was getting colder and emptier. And then, after growing this way for a very long, possibly infinite amount of time, most of this energy got converted into matter and radiation, which triggered the Big Bang. The Big Bang was the moment when the whole universe was squeezed into a tiny, super hot, and extremely dense ball we call a singularity. And all of a sudden, when it was less than 1 second old, this tiny ball started to unpack at speeds we can't even imagine. It was so hot that particles were moving extremely fast, crashing into one another and creating pairs with their opposites, like matter and antimatter. When the universe was 1/100th of a billionth of a trillionth of a second in age, it experienced an incredible burst of expansion that we know as inflation. At that moment, the universe doubled in size at the speed of light. And after that, it doubled in size at least 90 more times. growing from a subatomic-sized formation to a Gulf-sized structure almost instantly. After this burst of inflation, according to NASA, the growth of the universe continued, but it slowed down. As the universe kept expanding, it started to cool down, and matter formed. 1 second after the Big Bang, and the universe was already filled with neutrons, protons, electrons, anti-electrons, photons, and neutrinos. If we somehow managed to observe the universe when it was just a trillionth of a second old, we'd see that it was the size of Earth's orbit around the Sun. When the universe was a mere 1 second old, it was too hot for nuclear fusion to occur. At that time, its radius was just 10 light years, which is enough to enclose the 9 nearest star systems we know about. When the universe was 1 year old, it was smaller than our home galaxy and unbelievably hot. Finally hot enough to start nuclear fusion. When the universe was 3 years old, it was roughly the size of the Milky Way galaxy. When matter started to dominate radiation, which happened when the universe was around 10,000 years old, the size of the universe was about 10 million light years. It would be easy to think of the Big Bang and the resulting expanding universe as an ordinary explosion, where everything is expanding from a central point. But it's not a good analogy. There's a better one. Look at the surface of an inflating balloon. It'll be a two-dimensional equivalent of our three-dimensional universe. The balloon fabric will be space. These dots marked on its surface will represent galaxies. You see, they're moving apart as the balloon expands, but it happens only because the fabric, representing space itself, is expanding. The galaxies aren't moving on their own, and there's no central point for the expansion. The balloon is expanding into the third dimension, and that's where the analogy is getting trickier. Does it mean that our universe is expanding into some higher dimension? If there's no larger multiverse and our universe is all there is, then there's nothing outside of it. Not even a vacuum, which is still part of space. It means there's no point in asking what the universe expands into. If there was a two-dimensional being on the surface of our expanding balloon, they would be able to observe all distances in its surface 2D world getting larger. But they wouldn't see the third dimension into which the balloon is expanding. The same goes for us. Three-dimensional creatures. We see the distances between galaxies growing, meaning the inflation of space, but we can't perceive additional space dimensions into which the expansion is moving beyond our three. Even if space is indeed expanding into some higher dimension, our current knowledge of physics doesn't allow us to find out anything about it. It's likely to be beyond our comprehension.
We finally know when Earth will cease to exist. It'll happen when the Sun enters its red giant phase. Are we going to survive long enough to witness it all? Let's figure it out. In 5.4 billion years from now, our star, which is a yellow dwarf at the moment, will run out of hydrogen in its core. The Sun's core will heat up and become denser, causing the star to grow in size and turn into a red giant. The expanding Sun will get so huge that it'll encompass the orbits of Mercury, Venus, and probably Earth. Even if our planet survived being consumed on the spot, it'd still end up so close to the heat of the newly born red giant that it'd scorch our planet. No life would be able to survive there. At the same time, there might be another outcome. As the Sun expands, Earth's orbit might change too. You see, when our star reaches the final stages of its stellar transformation, it will lose unimaginable amounts of mass through extremely powerful stellar winds. It'll keep growing and losing mass, making the planets of the solar system spiral outward. So can it help Earth escape its dooming grasp? According to astronomers' calculations, our planet will not survive the expansion of the Sun in any case. By the time our star reaches its largest radius, which is going to be 256 times its current size, it'll be down to a mere 67% of the mass it has now, and the expansion process will be very rapid. The Sun will sweep through the inner solar system in only 5 million years. At one point, it'll enter a short helium-burning phase, which will last around 130 million years. During this time, it will expand beyond the orbit of Mercury. After that, the Sun will swallow Venus. By the time our star approaches Earth, it will be already losing as much as 8% of Earth's mass every year. Speaking of our planet's chances, we've got some kind of a good news, bad news situation on our hands. The bad news is that our planet won't be able to live through the expansion of the star. Even if Earth's orbit became 50% more distant from the Sun than it is today, it'd still have no chance. The Sun would engulf our planet even before reaching the peak of its red giant phase. After that, the star would still have 500,000 years and 0.25 AU to grow. Once Earth is inside the Sun's atmosphere, it will start colliding with particles of gas. Its orbit will begin to decay, and the planet will spiral inward. If Earth was just a bit farther from the Sun right now, at 1.15 AU, it would survive the expansion phase of our star. But what can be considered good news in such a tragic situation? Well, long before the Sun enters this red giant phase, the habitable zone around it will be gone. The heat from the Sun will evaporate Earth's oceans, and solar radiation will blast away the hydrogen from the water. Devoid of its main source of life, Earth will eventually become molten. It doesn't sound like good news, that's true. But the upside of this situation is that humanity will be bound to leave our planet long before it gets swallowed by the Sun. We just won't have a choice. Of course, we can't be sure that some other catastrophic event won't claim us before we have time to colonize some other world. An additional benefit of the changing boundaries of the Sun's habitable zone might be the restructuring of the entire solar system. Even though Earth won't be in our star's habitable zone anymore, most of the outer solar system will be. This zone will stretch well into the Kuiper Belt, which means that the formerly icy worlds will melt and liquid water will appear beyond the orbit of Pluto. So maybe that's where our new home will lie. Black holes are ruthless. They can swallow asteroids, comets, planets, and even stars. But can a black hole consume the entire universe? Almost any black hole was once a massive star that collapsed in on itself and became incredibly dense. Black holes have immense gravitational pull. Even light can't escape their clutches. The idea that a black hole can swallow the universe is based on a common misconception. People often think that black holes work like vacuums, pulling space inside. But that's not the case. Black holes can only swallow stuff that is extremely close, usually space objects venturing into their event horizon. That's a black hole's point of no return. Once you cross this border, there's no escape. The event horizon for a black hole with the mass of our Sun could extend a mere 2 miles. If a tiny black hole had a mass of our planet, its event horizon wouldn't stretch for more than a couple of inches. It would be the size of your thumb, no more. But a black hole's gravity still affects the stars and planets surrounding it. It might make them orbit, just like the black hole at the center of the Milky Way galaxy does. But the hole doesn't swallow them. If our Sun somehow transformed into a black hole with the same mass, which is highly unlikely, Earth wouldn't feel any difference in the gravitational force influencing it. Our planet wouldn't change its orbit or hurtle toward the newly born black hole. Of course, it would get very dark and freezing cold, but being pulled inside a black hole wouldn't be a concern. Plus, most black holes are quite small. A black hole can only swallow a star if the said star is aimed almost directly at the black hole. Theoretically, it might happen. But according to space experts, for the Sun to get swallowed up by a black hole at the center of our home Milky Way galaxy, a truly enormous amount of time would be needed. After all, the star's orbit would need to line up with the black hole in a very precise way. Even the largest black hole in the universe that we know about, a space titan called Ton 618, seems to be near the theoretical limit of how large black holes can grow. This limit is determined by the fact that black holes release tons of radiation while developing. This radiation heats up and ionizes the matter surrounding the black hole, which makes it more difficult for the dust and gas to cool down and fall into the black hole. As a result, it slows down the rate at which the black hole can feed. We can probably say that this self-regulation stops black holes from gobbling down entire galaxies, let alone the whole universe. And we shouldn't forget about the expansion of the universe either. objects in space move farther apart, which makes it less likely for them to collide or get captured by a black hole. If a black hole were to consume the entire universe, it would require a tremendous shift in the direction in which space seems to be moving. So, you don't need to worry that one day, our whole world will disappear inside a huge, universe-swallowing black hole. Unless, of course, the universe is already inside a black hole. I'm not kidding. There's a theory that we might be living in a black hole. Think about this. What if a black hole already engulfed us long ago? Surprisingly, some physicists deem this theory pretty plausible. For example, Dr. Nikodem Poplawski, a theoretical physicist from Indiana University, states that everything that a black hole swallows may turn into a new universe inside the hole or on the other side of it. So who knows? Perhaps our universe used to be quite a different place until it got pulled into a black hole.
Before J. Robert Oppenheimer ended up as the leader of the Manhattan Project, he was one of scientists studying nuclear physics under some of the most extreme conditions you can only imagine. By that, I mean the gravitational collapse of the most massive stars in the universe. Oppenheimer was part of the first team ever to determine the upper bound to the mass of cold, non-rotating neutron stars. Stars more massive than that limit collapse into a black hole. A star is an enormous collection of mass, dominated by hydrogen and a substantial fraction of helium, as well as some amounts of other elements. Its ginormous force of gravity works non-stop to pull all that mass inward. And the question here is, why don't such objects gravitationally collapse? For example, a star like our Sun has around 300,000 the mass of Earth. At the same time, it's only about 1/4 as dense as our planet. There must be some kind of internal force generated within the star itself and pushing back against gravitation. Scientists have been studying stellar evolution for many years. And here's the basic picture. In the majority of stars, pressure comes from thermonuclear reactions, due to which stars glow. In thermonuclear reactions, light elements are converted into heavier ones, and energy is released. When a star is running out of light elements, it has two options: to become a red giant and then a white dwarf, or to explode as a supernova and then become a neutron star or black hole. Most astronomers eventually came to the conclusion that under the extreme pressures and temperatures, a series of nuclear reactions could occur, leading to hydrogen nuclei getting converted into helium nuclei, releasing energy in the process. This released energy would provide huge amounts of outward radiation pressure, allowing most stars to shine for extremely long periods of time and holding them up against gravitational collapse. But unlike most scientists working on this problem, Oppenheimer was more interested in another aspect. What would happen to a star when it eventually exhausted its nuclear fuel it was burning to hold itself up against gravitational collapse? The scientists knew that without a source of fuel within a star, gravitation would gain the upper hand, and the core of the star would start contracting. There wouldn't be enough time for heat to be exchanged between the interior and exterior environments, and the same amount of heat would get compressed into an increasingly smaller volume. Today, we know that increasing the temperature of the helium-rich core of a giant star will release more energy than fusing hydrogen into helium, and stars as massive as the Sun eventually initiate helium fusion. But what happens when a star runs out of helium fuel in its core? Eventually, it'll stop emitting radiation too. The core will begin to contract, heating it up even more. Some stars, like the Sun, can't heat up enough to start any further nuclear burning reaction. So the core, mostly made of such elements as carbon and oxygen, contracts and contracts until there's no way to do it further. After all, there's a limit to how far a star can contract, and it's set not by the thermal radiation pressure of a living star, but by a certain quantum mechanical effect. No two electrons, an example of a type of particle known as a fermion, can occupy the same quantum state. That's why such types of stellar remains can hold themselves up against gravitational collapse. These remnants are physical objects nowadays known as white dwarfs. with higher temperatures and densities at their cores than at the exteriors. Still, there must be a limit to how massive a white dwarf can be. Beyond a certain mass, the size of this space object might be predicted to collapse to zero. Once a critical density is reached, either further nuclear reactions must take place, or a white dwarf must collapse further, which might lead to the appearance of a black hole. Oppenheimer chose to dwell on a different aspect of the problem, though. He asked, what would happen to the most massive stars, those whose temperatures and densities rose to unbelievable heights after they had burned through both their hydrogen and helium fuel sources? When a massive enough carbon core of a star contracts, it becomes so hot it can initiate carbon fusion, which leads to the creation of such elements as neon. As the neon core contracts and heats up, the burning of this element occurs at even higher temperatures. Eventually, it gets blasted apart by high-energy photons into oxygen. The core contracts and rises in temperature again, which leads to oxygen fusion and the production of such elements as silicon and sulfur. After exhausting all its oxygen, the core contracts even further, and silicon burning occurs. Sulfur, argon, calcium, iron, titanium, chromium, and nickel start building up, and the core becomes inert. A core collapse supernova follows soon. At that time, Oppenheimer didn't know such details, but he still came to an important realization. Any nuclear reaction would eventually run into a limit. The limit of having the entire core of a star behave as one single atomic nucleus. That nucleus would also have a limit of how massive it could be. If you compress a proton and an electron under high enough pressure and temperature, it will turn into a neutron through the process of electron capture. Oppenheimer's calculations were based on the Pauli exclusion principle. What is it? There are two types of particles. Bosons can be compared to extroverts. Imagine that you need to accommodate a lot of people in a hotel. Extroverts can be accommodated in a hostel. It will be fun, and they won't mind being cramped up there. But fermions are like introverts. If each room is a separate quantum state, then two electrons cannot live together. They need to be housed one at a time. This is the Pauli exclusion principle. Fermions, very roughly speaking, repulse each other. And this repulsion keeps the final stages of stellar evolution from collapse. Take a neutron star, compress it further, add some mass to it, and decrease its volume. At one point, you'll hit the same limit white dwarfs have. Oppenheimer reasoned that the same physical effects could come into play here. Whether you have a group of protons, neutrons, or electrons doesn't matter. They're all examples of fermions and obey the same principle. No two of them can occupy the same quantum state. This creates a pressure that pushes outward, preventing the stellar remnant, be it a white dwarf or a neutron star, from exceeding a certain critical value for its mass. The equation for that maximum mass value for the simplest model of a neutron star, cold and non-rotating, was first created by Oppenheimer and Volkoff. Today, it's known as the Tolman-Oppenheimer-Volkoff limit. According to it, the maximum possible mass for a non-rotating neutron star is somewhere around 2.2 to 2.9 solar masses. How do modern-day predictions that developed out of Oppenheimer's work stack up to the observations we have for neutron stars? Actually, very well. For example, the most massive neutron star with accurate distance and mass measurements is this millisecond pulsar. Although it rotates rapidly, it has a mass of 2.08 solar masses. In 2017, astronomers saw the first merger of two neutron stars ever. The combined mass of the stars taking part in the merger was around 2.75 solar masses. Those stars briefly formed a neutron star before collapsing into a black hole. And finally, in 2019, the second merger of two neutron stars was observed. But in this case, the combined mass of the two stars was around 3.3 to 3.7 solar masses. This time, the post-merger remnant turned straight into a black hole with no neutron star intermediary. It's a tricky feat to find the highest mass neutron star and the lowest mass black hole, since figuring out the properties of these objects is very difficult due to the fact that they're relatively rare. Plus, they're mostly located thousands of light years away from us and aren't known for being bright. Still, with constantly improving pulsar timing technology, the discovery of new neutron stars within the Milky Way, as well as neutron star mergers, sounds more realistic. Soon, we might discover where the neutron star / black hole mass limit lies. As for Oppenheimer, his most lasting contribution to the world might be developing a method for theoretically understanding the upper mass limit that defines the boundary between a black hole and a neutron star.